ganska mycket i Uppsala.
Men det är nog kul att göra någon gång.
Sorry for that message because I couldn't sleep last night because I had some kidney stones and it was very problematic. So I had a lot of painkillers and suddenly the pain was gone, so I told them that I would come, so that's why Tommy came here. And now the pain is a little bit back, okay? But then I have my notes with me. Hopefully if I am under the influence of the painkillers, I will copy and paste from here, okay? But I will try to do my best. Okay, so if you remember, we were talking about sequences in metric spaces. So now we want to talk about subsequence. So let me just describe it here for you on the board. So do you remember we have a sequence Pn, P sub n, and then it means that you can list them, P1, P2, P3, and etc. Okay? This is the list of, this is the sequence you have. But what do I mean by a subsequence? Somehow it is clear. I just want to choose some of them and bring them down and list them. And I want to call that a subsequence. But there is a rule that you have to respect. The rule is that you have, for example, if I decide to bring, for example, I looked at this one, I don't like it. I look at this one, I like it, I bring it down. But then if I change my mind, I am not allowed to bring P sub 1 down after P2. Okay, so whatever you bring down, what is coming next should be further down in the list. So for example, let me start. I don't like it, I don't like it, I write P3. If I change my mind and I say, no, I like P1, this is not the rule of the game. So you are not allowed to bring. But what you can bring here is at least P sub 4. But you can, for example, bring P10. But as soon as you bring P10 down, you're not allowed to bring any ones before. So you have to, these indices that you bring down should strictly increase. Is that right? So that's the meaning of a subsequence. Okay, so usually, if this is the informal but a very good way of looking at the subsequence. Another way to look at it is that these indices themselves are a sequence. So if you do not look at this P, what do you see? For example, let me write one of them later, P11, and then I decide to bring P20 down, something like that. And then don't look at P's. What do you see? You see 3, 10, 11, 20, etc. Yes? So this list, we call it indices for, sequence of indices. So this is a sequence. It is not a subsequence. Subsequence is the whole thing itself. But if you pick up the indices of your subsequence and arrange them here, this is called the sequence of indices. Okay? And the point is that all of them are natural numbers because that's the number. Okay? So in principle, this one forms a new sequence for me, which I call it n sub k, where k belongs to n. In this case, if I ask you what is n1, n1 is 3, what is n2, n2 is 10, and what is 11, 11 is n3, and etc. So for example, here, if I want to write this, instead of P3, I can write P sub n sub 1. Why? Because n1 is 3, and the first number in my subsequence is P3. So that's P sub n sub 1. And the next one, can you tell me what this one is? 10 is n sub 2, so P10 is Pn sub 2. Yes? And etc. So the next one is Pn sub 3. So usually, if you want to write a subsequence, if I have a sequence to be Pn with index n belongs to n, and then when I say a subsequence can be viewed in this form. But k belongs to n. Okay? And if I ask you what n sub k is, you will tell me n itself is a sequence. Because it is a sequence, its domain should be n. But in this case, the codomain is also n. And n sub k is what we say for n acting on k. Is that clear? So this is, if this is a sequence, this is a subsequence, okay? And then, for example, let us test your understanding a little bit. For example, do you think that N5, in general, not just in this example, what is the minimum value that N sub 5 can take generally, in general case? Yes? 5. Because when you say N sub 5, it means this is the 5th term in your sequence, and this sequence is just getting natural numbers. So this is the 5th one in the row. So in the worst case scenario, even if you start with 1, the next one will be 2, the next one. So this N sub 5 is greater than or equal to 5. So in general, if I write N sub k is greater than or equal to what? K. And then if I take the limit of N sub k, but I want to send k to infinity, what do you think will happen? Because this one is always greater than k. And if I take the limit and send k to infinity, this becomes infinity, and this is supposed to be greater than infinity, but there's nothing beyond infinity, so it becomes infinity. Okay, so remember that this sequence is a strictly increasing sequence of natural numbers. It is unbounded above. So when I send k to infinity, this becomes infinity. Okay, is that clear? For example, let us go immediately to the examples. Yes, I described this for you. This one. So do you think what I have written here is a subsequence? So for example, here I have written 7-3. So I have written just the normal sequence. Maybe this is not a very good example, but it is easy to understand. Okay, this is the sequence that I have. But then, for example, do you think this is an acceptable sequence of indices to define N sub k to be 2k? Do you agree that this is an acceptable sequence of indices? Why? Because the output is in the natural numbers, but also it is increasing. So if I put 1, I get 2. If I put 2, I get 4. If I put 3, I get 6. So it is increasing, okay? And it is increasing in the set of natural numbers. So if this sequence, I call it A sub n, okay, then let me call it P sub n. Then P sub nk, do you agree that in this situation, by this definition, is a subsequence? Yes, because N sub k has the properties we demand. So can you tell me, if I want to list this, can you tell me how should I list it? I put k equals to 1, so it becomes 2. So this becomes P2. So I choose this one and bring it down. Yes? If I put 3, it becomes, if I put 2, it becomes 4. So it means that I go to my sequence, pick the 4th one, and bring it down. Yes? If I put 3, it becomes 6, so I will pick this one. So this subsequence is the subsequence consisting of the even numbers. Yes? That's the subsequence. Okay, for example, the next one. The next one you can see. This is important. For example, can I define this like that? Can I define N sub k to be k over 2? No, why? Because even though it is increasing, but the output is not necessarily in n. I want two properties for N sub k. Increasing strictly, and the output should be inside n. So this is not, acceptable. But can I choose this one? Yes. And then, for example, for this sequence, if I want to write this one, let me write this mk this time. So what will be P sub m sub k this time? This will be, if I put k equals to 1, this is the first term, the next one will be 3, the next one will be 5, etc. Okay? So very simple. Let me see how many examples. So for example here, this sequence I have, this sequence minus 1 to power n. Can I say 1, 1, 1, etc. is a subsequence? Because this sequence generates what? Minus 1 to power n generates minus 1, 1, minus 1, 1, etc. Can I say the constant sequence 1, 1, 1, etc. is a subsequence? Yes. Because I am picking up this one, this is the second one, and this one is the fourth one. So I am playing according to the rules. Can I say -1, -1, etc. is a subsequence? Yes. But in this case, what is the range of this sequence? -1 and 1. But this is a constant subsequence. The range is 1, and that's a constant subsequence. The range is 5. Is that clear? Okay. So now, for example, I just give you a non-example. Do you think what I have written below this sequence is a subsequence? No, because first I decided to bring 3 down, then I suddenly started to bring 1 down. So I'm not allowed to do that. So I have to bring things in order. Okay, that's it. Okay. Is there something, the corresponding sequence is strictly increasing? Yes, I talked about that as well. Okay, now this is the first theorem we want to talk about. So now we want to talk about the convergence of subsequences. Okay, so what is your feeling? If you know that a sequence converges to P, so let me write it here for you. Let me change my chalk. So this is theorem 7.8. So what do I have? I have a sequence, I have a metric space. And what do I have? Pn is a sequence in n, in x, such that Pn converges to P. When I say converges to P, this P belongs to X. And now I have a subsequence of this sequence. Okay, that theorem is mentioned in if and only if form, but I am just going in one direction. So I have this metric space. I know that I have a sequence in my metric space that converges. If you want to imagine, this is your metric space, and this is a point P, and then you have a sequence converging to this one, for example, P. Yes, this sequence is converging to this P. Now, the point is that I pick any subsequence from the original sequence. We want to show that this subsequence will also converge to the same point. Is that clear? So, if that is the case, P sub n sub k, yes, k is a subsequence, is a subsequence. So what I want to prove, I want to prove that P n sub k also converges to the same P. This is what I want to show. Okay? So how should I prove this? Sometimes it might be easier for you if you change this to something new. For example, you can define a sub k to be P of n sub k, if you want to. Because usually our brain is used to having one index for a sequence. When I am working with subsequences, I have 2 indices, one after the other. It doesn't hurt if you give this a name, because at the end, your sequence, your subsequence depends on this counter k. So you can call it a sub k. And then what is the benefit of that? The benefit is that you can work with sequences with just one index. But if you are not confused, that is just a luxury. You can just work with the subsequence itself. Okay, so can you tell me, for example, if you use this idea, for the beginning might be it is good, my goal will be to prove this one. Yes? And this is what we learned yesterday. How should I prove that? I want to prove that a sequence converges to P. What do I say? I would say let epsilon be greater than 0. We prove that there exists, because this index is called k now, so there exists a k in the set of natural numbers such that if k goes beyond that capital K, then what happens? The distance from a sub k to p becomes less than epsilon. This is what I want to prove. I want to prove that I can always find a natural number so that if k goes beyond that natural number, the distance between this sequence and its supposedly limit is less than epsilon. Is that right? This is what I want to show. But what I have at my disposal, what do I have? I know that the original sequence converges to P. So we know that so P sub n converges to P. Okay? So what does it mean then? So because P sub n converges to P, this means that for every epsilon, including this epsilon, there exists a natural number n such that if n goes beyond capital N, then the distance between Pn and P becomes less than epsilon. Do you agree? This we know. This we want to prove. But can you see, so this we know we have it. So we want to prove that this, you see, I give you an epsilon. Because I know Pn goes to P, according to the definition, you can give me a capital N, which works in this way. What does it mean? It means if a natural number is greater than this given number, I can take that natural number and put it below here. So it becomes the distance between P sub n and P is less than epsilon. This I know. I am waiting for you to suggest for me what I can choose for K so that this will work. Can you tell me?
K equals to N.
N itself. Do you see that? Because, so here, clay. Of course, one possibility is that N equals to K, K equals to N works. Okay? So how should I convince you? I have to convince you in this way. I would say that let K be greater than or equal to capital K, which is N. We show that what? D of AK and P is less than epsilon. Okay, so K is greater than or equal to K, which is N. What can I say about N sub K then? Because you know that N sub K, we just learned it up there. And this is a very good relation when it comes, remember this. N sub K is always greater than or equal to K. I myself choose K greater than this N. Let me clean this. I choose K greater than N. But because N sub K is greater than K, what can I conclude? I can conclude that N sub K is greater than N. Do you agree with that? Yes? Now look here. If you know a natural number is greater than this one, you can conclude this by putting this little n here. So I will do the same thing. So I will continue and write D, I write P, I write less than epsilon, but what should I write here? I write P with this as an index, N sub K. And this is nothing except your A. So this means that A sub K. This means that D, A sub K, and P is less than epsilon. I really want you to sit down and work it out exactly, but intuitively it is very clear. Because if the whole sequence is going around this, what does it mean? It means that if I draw any circle around that with any positive radius, the ones that are left outside are finite. All of them will be, except those finitely many, will be here. And the subsequence is chosen from this list.
by dropping some of them and including some of them. Of course, it will be clear that all the terms of the sequence eventually will be in that circle. Intuitively, it is very clear, but if you want to write it down, you have to write it like this. So what we did, we want to prove the existence of this K. This is a question mark. What I know P sub n goes to P. So I know this n exists. And I claim that this K that I was looking for is exactly this n, which is granted by this assumption. And that is the claim, this is the proof of the claim. Is that right? Yes? Yes.
You state that it's an infinite subsequence.
No, subsequence is always infinite.
Okay, right.
Always. Sequences are infinite, subsequences are always infinite. There are infinitely many terms, I mean. Yes? Okay. So now, why the other way around is correct? It's just half a line. So if I have a sequence converges to P, okay, this is granted. If you pick any subsequence, you can pick infinitely many subsequences. All of them will converge to the same point. This is for granted, and hopefully you understood the proof. But now the other way around. If every sequence of a given sequence, every subsequence of a given sequence converge to the same point. So every sequence, so you have a sequence, this sequence has infinitely many subsequences. It turns out that all of these subsequences are converging to the same point. This theorem claims that you can conclude the whole sequence is also converging to the same point. But the proof is actually extremely simple, yes?
The sequence is a subsequence
Of itself.
So it's,
Do you agree? So what is this? So any sequence is a subsequence of itself. So because all subsequences are converging to the same point, it can also be said about the sequence itself as a subsequence of itself. Yes? Can you tell me in that case what is n sub k? In the case of sequence itself, what sequence of indices pick up exactly the same sequence itself? K. N sub k should be k. Yes? This is generating the sequence itself. Because if I put n1, it gives me the first term, n2, 2, n3, 3. So I'm just picking one of them after the other. Is that clear? It's a very, very important and simple theory. Okay, so this is a very good way. Do you remember? This is a very good example. We talked about -1 to power n. This is a very innocent sequence which serves us a lot. So -1 to power n, hopefully you know, do you remember it was divergent? And we had some kind of a proof for that. But now I think this is the best proof using this theory. Because when you see that you have this sequence -1, 1, -1, etc. Yes? Do you agree that -1, -1, -1 is a subsequence? Okay, it's a constant subsequence. Do you think that this converges? It converges to what? Minus. Do you agree that 1, 1, 1, etc. is also a subsequence of that? And you know it converges. But it converges to what? 1. So you can immediately say that this series diverges. Why? Because if it is supposed to converge, every subsequence should converge to the same point. But they are converging to different points. So it's a very, very important tool in your hand if you want to prove that a sequence does not converge. If you can come up with some subsequences that one of them converges to a point, the other one converges to a different point, then you can go back and conclude that your original sequence does not converge at all. Is that right? Okay. Now, let us go to this theorem. So I don't remember if I can prove them on top of my head, but let us see. Today I am a little bit busy. So, 710. Let us understand the problem first. So what do you have? You have a metric space. This is your metric space. And then you have a subset of your metric space, which is compact. And hopefully you remember, for this one, I still don't know what to do because it is open. But for compact, I know it is closed, if you remember the previous lesson. Okay, and then what happens? Then every sequence in K has a subsequence that converges to a point of K. Okay? So what does it? It is a very important tool if it is compact. So what do I have? It means that every sequence that you choose from your set, let us say one P1 up to Pn, even if it is not convergent, that is important. You have a compact set, you have a sequence which is inside this compact set, then you can always arrange to find at least one subsequence that converges to a point inside K. Yes, then every sequence in K, a random sequence, which is not maybe even convergent, but you can find every sequence in K has a subsequence that converges to a point in K. Okay? So, how do you think we will prove this one? Okay, so let me introduce a set to be the range of your sequence. So this is a sketch of the proof, okay? This is the range of the sequence. There are two possibilities that happen for this range. Either it is finite or it is infinite. So there are two cases. A is finite, A is infinite. Yes? So you see what I have? I have a metric space, I have a compact subset, and I have a random sequence within K. And now what I do, I consider the range of my sequence. It means that I actually drop the repetitions and put those elements there. There are two possibilities. Either this set becomes finite, for example, in this case, the range is finite, 1 and minus 1. Or it becomes infinite. For the finite case, do you have intuition the proof is finished? Let us say that this is finite. Okay? I am waiting for you to tell me intuitively a subsequence that converges. Do you understand what I'm saying? So the range is finite. I am telling you that for the case that A is finite, you can easily come up with your subsequence that is definitely convergent to a point in K. Yes?
The order is finite, then it should converge on like the final number of the range, no?
What is your subsequence? Because you need to offer me a subsequence with that property I asked you.
So isn't it just the range then?
Isn't it the
No, the range cannot be a subsequence because as I told you, the range might be finite. I'm talking about when the case that the range is finite. The sequence cannot be finite. Sequence contains infinitely many terms, even though many of them can be the same. But one thing is clear. How many terms you see infinitely many? But if there are infinitely many, but when you put them as a range, it becomes finite, it means what? It means at least one of them is repeated infinitely many times. Is that right? Because if all of them are repeated finitely many times, then of course this will be finite. Is that right? So it means that at least one of these numbers is repeated infinitely many times. Yes? Is that right? If this range is finite. Yes, is that clear? Okay. So for example, in this case, you see, what is my range for this case? Is minus 1 and 1. Do you agree this is finite? So I am telling you at least one of them is repeated infinitely many times. In this case, both of them are repeated infinitely many times, but one of them at least should be repeated infinitely many times. Okay, and that gives you your subsequence. Because, for example, in this case, I start moving through my sequence. Whenever I reach to the number that I like, I bring it down. But because there are infinitely many of them, this process will not end, and I will choose a subsequence finally. Is that clear? Okay, so for this case, we are done. By the way, and of course, I have to show that this is a subsequence that converges to a point in K, of course, because all of them are in K, so that constant number will also be in K. But now A is infinite. It's a little bit harder. What happens if A is infinite? You need to remind yourself about something we learned in metric spaces. Do you remember So where is A? If I want to draw A is here. This is your A. Okay? So in this case, you see that in this case, I am talking about this case. So A is a subset of K. K is what? Compact. And then A is what? Infinite. Because I'm considering this case. Yes? Do you remember a theorem like this? If I have an infinite subset of a compact set, what could I say? It has a limit point in K. So this means that, because I don't remember which theorem was that, but I can conclude A has a limit point P in K. A previous theorem, I don't want a previous result. I hope that you trust me, okay? But then what can I find for my subsequence now? We had it yesterday. You remember I told you something. I told you that if this is a metric space and if you have any set, doesn't matter there, and if you have a limit point, I can always reach to this limit point by a sequence within the set. This was the result we had yesterday. Okay? If I have any set of a metric space, and then P is a limit point for A, then I showed for you that you can always find a sequence inside A that takes you to the limit point. Okay? Okay, so we are done here, more or less. Yes, do you agree? Because now this is my limit point, which is in K. And what do? A limit point of A, which is already in K. So then I can have a sequence that takes me to A. Yes? Yes, we're done. Because this is my set, actually. A is my set. The set of all these terms. Yes? Because you see, A itself, there is nothing outside. This is not a very good picture. A is only consists of these points. Okay? So it means that from these points, I can go towards this P. Okay? And that is my subsequence. Because I am picking elements from this list. Do you understand what I'm saying? Yes or no? Yes, because here, when I say that P is in K, P is here, and I am saying that in A, what is A? A has nothing except these points. And I'm saying that with these A's, you can approach to P. It means that you can pick up elements from this list, and this automatically becomes a sub-list or subsequence. Is that clear? Okay. So now let us go to the next one. So this is also a very important result to remember. Proofs are good if you know them, but Bolzano-Weierstrass theorem in R to the K. So every bounded sequence in R to the K has a convergent subsequence. Okay? Why is that? Do you remember what was the importance of Euclidean spaces? So in Euclidean spaces, Heine-Borel theorem tells you what? We know something about compact spaces, yes? They are closed and bound. So if I am working in Euclidean spaces, compactness is equivalent to being closed and bounded. Do you remember something like that? Okay, but let us see if we can prove this one as well. Every bounded sequence in R to the K, every bounded sequence in R to the K has a convergent subsequence. So how can we do that? 711. Yeah, 711 takes me for coffee, yes. Okay, so how we should do? Do you remember what is the meaning of a bounded sequence? So let us say that Pn is a sequence in R to the K and bounded. So what is the meaning of a bounded sequence? Do you remember we talked about that yesterday? In the case that we are working in the real line, being bounded is not very problematic. Why was it? Because we have the notion of order in R. But if we go to higher dimensions, we don't have the notion of order. If I have 2 points in plane, I cannot say this point is smaller than that point or the other way around. There is no notion of order. So we define boundedness intuitively by putting it into a circle, something like that. So if you remember these things, you can construct the definitions. Otherwise, it would be very hard to extract everything from your memory. Okay, so when you say this is bounded, what does it mean? It means there exists a cube in R to the K, yes, such that for f, and there exists a positive m, such that for every n in n, the distance from Pn to that fixed cube is less than or equal to n. That's meaning being bounded, okay? Okay, now let me ask you this question. I will define a set for you consisting of all elements from R to the K such that the distance of that x to q is less than or equal to n. Yes, let me see if I have done it right. Yes. Okay, so first of all, do you agree that this set is bounded? Yeah, the set bounded. K is bounded. But do you agree that this is also closed? Why? Because of this equality, it contains the boundary. So it is also closed. Can I immediately, do you remember, can I immediately jump and conclude that K is compact?
Yes.
No. In general, no, but in R to the K, yes. That is important to remember. So K is also a subset of R to the K. Then I can use Heine-Borel theorem and conclude that K is compact. Yes? So K is compact. Okay. So now I want to show that this sequence, which is bounded, has a convergent subsequence. Yes?
We should just use the previous theory.
Yeah, exactly. That's the previous theory. So the result is concluded from the previous theory. Yes? You remember what was the previous theorem? The previous theorem tells me that if I have a compact subset, every sequence in K has a subsequence that converges to a point of K. Yes? Like if you combine this with that result, you work. Is that clear? Yes? Now we come to a very important result of the Cauchy sequence. That's a very important one. We have a little bit of time to start. So, what is a Cauchy sequence? And what was a convergent sequence? A convergent sequence was a sequence that if you go to the tail of the sequence, finally all of them will gather around a point of convergence, eventually. Yes? But Cauchy sequences are not defined based on one single point of convergence. The Cauchy sequence intuitively means that after some point, if I go to the tail of my sequence, they are getting close to one another, not necessarily to a fixed point. Okay? And then might be you can say that, okay, you can work on your intuition, by the way. For example, do you think if a series converges, what does it mean? It means eventually the points are getting close to a fixed point. Intuitively, when I say intuitively, there is no intuition in metric spaces unless we are working in Euclidean spaces. Intuitively, in the Euclidean space, it seems that if they are gathering around one fixed point, getting close to one fixed point, based on what we know from this Euclidean space world, those points should also get close to one another. Yes?
Yeah, because
Do
they're
you
getting,
agree?
yeah, of course.
So somehow it seems that convergent sequences are also somehow Cauchy in the sense that I will define it shortly. But I just defined it for you intuitively. It means that after a point onward in the sequence, all the terms are close to one another, okay? But what do you think about the other way around? I was trying to visualize it, it was hard for me. Do you think that if after some point all the points are getting close to one another, can we guarantee that they are also getting close to one fixed point? So that is the importance of this topic. Okay, one of them was intuitively very clear. If they are getting close to one fixed point, apparently they are also getting close to one another. But if the points are getting close to one another, are they really getting close to a fixed point somewhere? So this is something back in, it should be in the back of your head, okay? But let us have this curiosity, but let us define it properly. Now, can you define it for me properly yourself? You understand the idea. I give you a sequence, 7.2, 7.12. So what we do, we say that I have a sequence in a metric space, and I have a sequence there, okay? When do I say that this sequence is Cauchy? Can you define it for me based on the intuition? We say that this is Cauchy, Pn is Cauchy, if what happens? If after some point onward, the terms are getting close to one another. What does it mean? It means for every epsilon greater than 0, you can find a natural number n so far is exactly like convergence, such that what happens? If m and n are two indices greater than or equal to n, then the distance between p sub m and p sub n becomes less than epsilon. Okay? So this means if you give me any epsilon, no matter how small that is, the only constraint is being positive, then I can give you a natural number so that if you pick two indices from n onward, the distance between those two terms is less than epsilon. That's the meaning of being Cauchy. Is that right? Okay, before going further, I want to do it for the very important case of real numbers. So let us say that instead of this x, I have R now. And D is the Euclidean metric. Can you define what is the meaning of Cauchy again? Very clear, yes? This will be the same. This will be the same. And this will be the same. What will be different? The distance will be Euclidean distance, which is the absolute value. Yes? Understandable? Okay. So now let us go to the next. This is a typical, this is a good example. Of course, no one will do it in this way that I want to do, but I want to use definition. Have I mentioned that? No. Yeah, so because if it comes to the exam, by the way, if it comes to the exam, if you understood what I said, why this is Cauchy?
Because it will approach to 1.
1, because it is convergent. Later, we will prove that every convergent sequence is Cauchy, and you already know this is convergent, so no one will actually, unless I force you in the exam, that use the definition. Otherwise, this is the simplest way. Okay, but let us, I want you to learn the definition as well. So let us do this one as well. Okay, so this sequence is given to you. A sub n is equal to 1 plus 1 over n. We want to use the definition and prove this is Cauchy. So what do? You start with a typical sentence. You would say, let epsilon be greater than be given. Okay, so what should I want to, what I am supposed to prove? I am supposed to prove the existence of a natural number there so that if two indices m and n are greater than or equal to n, then it gives me, because I am working in Euclidean space, can you tell me what should I write here? So let me show you. Yes. Because I'm working in Euclidean spaces, what should I write? 1 over n minus 1 over n.
Yes.
It is a sub m minus a sub n. Yes? A sub m means 1 plus 1 over n. Yes? Minus a sub n, which is 1 plus 1 over n. Do you agree? Okay. But there is a simpler way to write this down. So what is that? 1 and 1 are cancelled, and I get absolute value of 1 over m minus 1 over m. Okay? So what is my goal? I give you epsilon as your teacher, and then you as a student are supposed to propose me n. But as soon as I give you this epsilon, I lose control over epsilon. Okay? I gave you epsilon, finished. I am waiting for you to do something and find and give it back to me. And I told you yesterday, don't try to be optimized. You just need to find something that it is guaranteed to work, not the best one to work. Okay? So this is extremely important. Because if you have this in the back of your head, mainly you know what to do. For example, I will come here. I don't know if it is a scratch paper or not, but I will try to write it down. Okay? It's not a scratch paper, it's part of the solution. Do you agree that this is less than or equal to 1 over m plus 1 over n? Yes, because that's the triangle inequality. Yes? So, but now my goal is to make this smaller than epsilon. I ask myself, if I can make this one smaller than epsilon, my goal is achieved. Yes? Because I don't want to do it in the best way. I want to guarantee it. Okay? So I am saying that this is something I know. My goal was to make this one smaller than epsilon. But if I succeed to make this one smaller than epsilon instead, I achieve my goal as well. Do you agree with that? Okay. This one is easier than work with absolute value. Okay, so 1 over m plus 1 over n. Can you guess this n? In thinking this way, make this one less than epsilon over 2. Try, this is a scratch paper now. And try to make this one also less than epsilon over 2. Because if I manage to make both of them less than epsilon over 2, then the sum of them will be definitely less than epsilon. Do you agree? Okay. But now, remember, m and n are supposed to be greater than n, and I have, as the student, I have control over n. So, can you tell me, let n be a natural number? I want to wait for you. Number such that I will write n is greater than the question mark. Anyone else? If I make n greater than something that you're supposed to discover, then because m and n are supposed to be greater than that n, it will be automatically greater than the question mark. But you want to design this question mark in a way that each one of them, 1 over n, becomes less than epsilon over 2. So, yes?
Such that n is greater than 2 over epsilon.
Yes. Do you agree? Because if I choose n greater than over 2 epsilon, then what happens? 1 over n becomes less than epsilon over 2. And because m is greater than n, 1 over m, so let me write it like this. Then 1 over m plus 1 over n, let me write it for you, since m and n are greater than or equal to n, then 1 over m plus 1 over n is less than or equal to 1 over n plus 1 over n. Do you agree? M is greater than n, so 1 over n is less than 1 over n. N is greater than n, so 1 over n is less than 1 over n. But 1 over n plus 1 over n is 2 over n. Yes? And then this becomes less than, if I multiply it by 2, which becomes epsilon. Understandable? Okay. And then you see that it is not always obvious if this expression is complicated. It's not obvious to come up with this. Okay? But anyway, this is one exercise that you just directly prove that this given sequence is a Cauchy. Because as I told you later, there would be a simpler way to do it. Any questions? Okay, so let us have a break for 5 minutes and then we can continue.